Welcome to Pre-Calculus. Today we will investigate graphing transformations of power functions, focusing on connections between the transformation equation and the changes it makes to the parent function's graph. Let's take a look at one example. So we've got a power parent function here, f of x equals x to the power of 5, so the quintic power parent function. And then I've got a transformation rule, negative 1/3 times f at x plus 1 in parentheses minus 2. So we want to describe the changes that that rule, the transformation, makes on the parent function's graph. And then we want to follow that up by graphing the transformation from a table of at least 5 coordinate points to check our descriptions. Did we describe the transformations correctly? Well, let's begin by looking at the parent function's graph, and then we'll say what are these changes that the transformation rule makes on that graph. But let's create a table of values for that quintic power parent. So it's x values, we'll go -2, -1, 0, 1, and 2. Those traditional values for a parent function. Notice they're centered around the origin, and then our function is x to the 5th. So we'll calculate these. It's quick to calculate y values for the parent function. So I'm going to put in -2 in parentheses to the power of 5, and that's -2 times itself 5 times. So remember, I can pair up those factors, and there will be 2 pairs that multiply to +4. But then there's a spare -2. So just in terms of sign, it's going to be negative, positive times negative. And then 4 times 4 is 16 times -2, -32. So I see, because it's an odd power, the negative sign is preserved. So -1 to the power of 5. I want to expand that one, but it shows the same patterns. That's going to be -1. Once I reach 0, it becomes easier. 0 to the power of 5 is just 0. 1 to the power of 5 is just 1. And then 2, I could put it in parentheses, but really it's all positive. So that's just going to be +32. Notice that we do have that odd function symmetry, the same numbers but opposite sign around the origin. So I want to graph that one so I can see what's the parent function look like. So the first points I can graph are -1, -1, 0, 0, and 1, 1. The others at -32 and +32 are off my graph. But I can represent that by showing that it's very steep ascent and a squared off area towards the origin there where it has its inflection point. So that's the parent function. So what we're doing now with this transformation rule, and let's highlight it here in the green, is I want to say, what do these pieces do to that graph that we just put on our coordinate plane? How do those values around f of x change the red graph? So I want to do that piece by piece, and let's kind of itemize what we're looking at. So I'm going to start by taking this function transformation rule, and I want to apply it to the actual f of x equation to write our transformation equation. So I'm going to call our transformation g of x, since the parent is f of x. And I'm going to write the pieces around the function just kind of in place. So the -3's just out front, multiplying times the function, which is f of x. I see that within the function part, the domain has changed from just x to x plus 1. So I need to put that x plus 1 in the parentheses and then raise the parentheses group to a power of 5. And then the -2 is on the outside of the function, so I'm going to write it tacked onto the end there. So that would take my transformation rule and apply it to the function equation to give me my transformation equation. So from there, what I want to do is say, what are these pieces changing to that red graph? So I'm going to start on the inside of the function. When I add 1 there, remember from previous transformation work that you may have done that value, if it's added or subtracted to the x within the function, so inside the parentheses there, that is a horizontal shift. So I'll do a left-right arrow and say that's a shift. But we go opposite the sign. So if that's saying +1, typically we would assign positive to a right-hand shift. But if we're going opposite the sign, what we would say is, hey, that's going to shift the graph left 1. So I'm going to put our actual descriptions here in red. Left, and I'll put it as an arrow 1. The second change that I want to see is this number added or subtracted outside the function. So that -2, the way we would describe that generally is that's a vertical shift, an up or a down shift. And unlike that horizontal shift where we go opposite the sign, here we follow the sign. So if I'm seeing a -2 on the outside, minus is in the down direction vertically. So I'm going to predict this has a shift down 2. So there's 2 changes we've noticed. So the parent function is going to shift 1 to the left, down 2. Those 2 changes don't change the actual shape of the graph. They just are slides on the coordinate plane, but the actual shape is preserved. But the next change we would notice actually does change the shape. So in the pink here, I want to highlight this coefficient of 1/3. Notice I'm taking it separate of the negative. I want to describe those separately. This value is what we would call our A term. If that A, like this one, is between 0 and 1, that's going to be a compression on the graph vertically. And what that will look like is it'll make the graph flatter and fatter. This is what we would call a compression. There is the possibility that that value could be greater than 1. And if that's the case, so it's not what we're seeing here, but if you were to run into that, where it was like, for instance, a coefficient of 2 or 3 or 100, that's the opposite. It would be a vertical stretch, and the graph would become a lot narrower and thinner. So since we are seeing our A value is 1/3, it's between 0 and 1, what we would say in terms of our prediction is this is a compression by a factor of 1/3. It's a compression by a factor of 1/3. So that is actually going to change the shape of the graph. What we see here in red is in that compression going to get flatter and kind of spread out. The last change that we can notice here is that negative sign. So I'll highlight that in the yellow. And notice that's really the last thing that's changed the actual function equation. That negative out front, and I'll draw an arrow here because I'm running out of room, is a reflection. And you can think basically it's going to turn all the y values opposite sign. So it's going to be a reflection in the x-axis. So it's as if I took my graph and flipped it over the x-axis. And since we actually have that here, I'm going to actually say just that. It's a reflection of our graph across or in the x-axis. So 4 changes there. The cool thing about this is I can kind of sketch a prediction before I go to actually graph g of x, that transformation. So the point I would track for the left and the downshifts is that point at the origin. We call that the inflection point. So I'm going to track the inflection point, and where it would land if I'm shifting it 1 left, down 2, my new inflection point will be there at -1, -2. The other change that we saw was that the graph would be compressed. So it's going to be flatter, but it's also going to flip over the x-axis. And so what I would expect to see is some graph that's got a flatter shape, it's more spread out, but also the end behavior swapped, because when I flip an odd polynomial or an even across the x-axis, it's going to flip our end behavior. So on the original, the one in red, the left side is tending towards negative infinity in the y. On the right side, it's tending towards positive infinity. That switches in my transformation. Well, those are my descriptions. Let's follow it up by actually graphing g of x by our equation. I think I should probably include -3 if our graph is shifted one to the left. So I'm just going to go -3, -2, -1, 0, 1. Probably don't even need to go to 2. And that function is the g of x function that we wrote there. So I'm going to write it here. It's -1/3 parentheses x plus 1 to the power of 5 minus 2. What I'd like to do is go get a table of values for that one. So let's head over to Desmos to get our table. And I'll start just by inputting the function in the entry. So we've called this one g of x equals -1/3 parentheses x plus 1 close parentheses to the power of 5, and then on the outside minus 2. And I can see that the graph shows those changes. It kind of matches my predicted transformed graph that I put on my coordinate plane. But let's get a better graph by getting a table. So I'm going to include -3 there. And you can see it's been multiplied by 1/3 because we've got all these repeating 3s or repeating 6s. So I'm going to grab, yeah, and I can exclude 2 because at -83, that's off my graph. So I'm going to pick up these 5 coordinate points, -3, 8 points repeating 6, -2, -1 point repeating 6, -1, -2, 0, -2 repeating 3s, and then 1, -12 repeating 6s. That's what I need from Desmos. I'm going to head back to my notes screen to finalize my graph. So let me fill in our table here with what we saw. So 8 point repeating 6 is at -3, -1 point repeating 6, -2, -1, -2. Notice you can see that left 1 down 2 in that inflection point because it was at the origin to begin. 0, -2 point repeating 3, and then 1, -12 point repeating 6. That's probably off my graph, but let's see how our prediction went. So -3, 8.6, so right there. -2, -1.6, so that's actually pretty close to the prediction. Inflection point's right on. That one's easy to track. 0, -2 and 1/3, and 1, -12. So I can try here, if I shrink the view, to include some lines to get down to -12. So -9, 10, -11, -12. So that's going to be about there. So it looks like my prediction there was a little too compressed, but it gave the idea. Let's put the precise graph in. And I'll erase the prediction. And there we go. We've got our transformed graph to prove that we describe those changes in the equation about how they're going to change the parent function's graph. Thank you for joining for this investigation of transformations of power parent functions. I'll let you go describe and prove those changes for your own power parents. I'll see you soon.